Okay, let's get started. So yesterday, or not yesterday, Monday, we started talking about limits. And they already sort of feel familiar because we've been working so much with collapsing collections and limits are defined using collapsing collections. So what we're going to do today is we're going to define a few more flavors of limits. And we left off with this one yesterday, so we'll do an example. And then what we're going to do is also talk about sequences and limits of sequences right now. The reason for that is because we will need them later when we are setting up the definition of an integral. So that will come again. We're going to talk about them briefly today, and then they'll appear again in like a month. And then on Friday, we're going to introduce some tools for actually like calculating limits. And those tools will also help us to say that functions are continuous, and they'll be a lot easier to work with than collapsing collections. So we've like worked really hard to set up the foundations, and we'll use that to, give some rationale as to why these tools that we're going to introduce on Friday work. But starting Friday, everything will get a lot more like computational, and we'll be like moving away from collapsing functions. Okay, so let's start with just like recapping this definition. So we're looking at limits, like infinite limits, so where the output is infinity. So we say that the limit as x approaches a from the right of f of x is infinity if, so what we're going to do is start with a right-sided collapsing collection for a, right, because we're approaching a from the right. And we're going to feed that into f and take the wrappers, and then what we want to see is a collapsing collection for infinity. So the limit as x approaches a of f of x is infinity if, when we apply f to a right-sided collapsing collection for a and take the wrappers, we get a collapsing collection for infinity. So let's do an example. Let's look at the function f of x is 1 over x squared. And let's look at this at x equals 0. So we'll look at the limit as x approaches 0 from the right of 1 over x squared. Okay, so of course this function isn't defined at 0, but we can still look at its limit and ask what is the function moving as we get closer and closer to 0. So if you think about what's going on here, we're putting really, really small numbers into x squared. And so 1 over that number is going to get really, really big. So we might guess that this is going off to infinity as we put in smaller and smaller values for x. So let's show that this limit actually is infinity just using the definition. So first we need to start with a right-sided collapsing collection for 0. So I'll just use the standard one. We'll take the interval from 0 to 1, 0 to 1/2, 0 to 1/3, and so on. Okay, so now we have to compute the f images. And maybe this is a little bit tricky in this case. So what would the f image of the interval from 0 to 1 be? Yeah. Yeah, how did you get 1 to infinity?
Yeah, so right, so this is gonna be when we plug that in, that's gonna be the smallest value. So that'll give us the left endpoint of the interval. So 1/1 squared gives us this 1. So this is 1/1 squared. That's how we got that 1. And then yeah, so as let's say just to like be precise about this, y is every number larger than 1 contained in the output of f. So let's let pencils. So let's let a be some number larger than 1. So I'm claiming that the f image is this whole interval. So a should be the output of something. So if a is greater than 1, then 1/a, sorry, let's just do it this way. So 1 is less than 1/a, and 1/a squared will be even less than that. So that means that if I stick this into f, sorry, I'm getting all turned around. So what number would I need to plug into f to get a? So it would be like probably 1/, I'm just going to guess and check, 1/√ a. So if I plug that into f, I get 1/, the square of 1/, square root a, which is, this will be a, right? Okay, so what I want to argue is that 1/, square root a is between 0 and 1. Is this true? Yeah, because we can just square this entire inequality. So I get, oops. Right, so we have this, we want to show that this inequality is true, but this is true precisely because we took a to be greater than 1. Okay, so I feel like that was kind of a mess, so let me recap. We wanted to show that given any number in this interval, there is a number in this interval such that f of that is equal to the number that I took from this interval, which is a. And my guess was that if I plugged in 1/square root a, that would give me a. And that worked out. And so then the only thing that was left to show is that 1/square root a actually came from this interval, which is true because of this. Okay, so that tells me that the f image is actually 1 to infinity. And then the pattern continues for these other intervals. So what I mean by that is that to find the successive f images, I just need to plug this number into f, and that will give me the left endpoint. And then the rest of the interval goes to infinity. So here's the other f images. So we had 1 to infinity. Next one would be 1/1/2 squared, which is 4 to infinity. So this is, how did we find this? This is 1/1/2 squared. Just applying f to that right endpoint. And then the next one would be 9 to infinity, and so on. Okay, are there questions? Yeah.
So what I don't understand is like, I understand that the 0 is plugging that in is what's giving you infinity. But like plugging, for example, like the 1 in is getting 1. But how can you like swap it? Because like in the original interval, it's like the infinity technically would be like on the left side, which obviously like infinity is greater than one, but like, is it fine to just totally swap your F image so it's like,
So for the interval, you just always write the smaller number on the left and the bigger number on the right.
it doesn't matter that you're like switching it from the original?
Yeah,
Okay.
that's, yeah. Are there other questions?
It's just, so, I understand how when you do like the wrappers of the outcome of the students, I understand how I can show you like limit, right? But like, is it really for continuity very well, right? Because like, what if there's just a removable this kind of code? Why is it really
So you mean taking like wrappers of the F images of a collapsing collection?
Yeah,
So if you have a removable discontinuity, that number will be in the F image of everything in your collapsing collection. So it won't collapse to a single number because it'll always be,
even if that number though is at like 0 exactly or something, like imagine like 0 just choose to 100, but everything else is just continuous, then it wouldn't catch with that, or maybe.
so you're saying, like, let's say we define a function that is 1/x² everywhere except at 0, we just add 0. Okay, and we want to see, is this continuous at 0?
Yeah.
So if you look at collapsing collections, they're gonna end up being a collapsing collection they won't be a collapsing collection for infinity. It'll be like, okay, let me draw a picture.
So,
I understand from like a lemon perspective, I just bring up what they call one class and class.
so it's looking something like this, right? So if I want to show that this is continuous, I'm taking a collapsing collection for 0, and then my F images would always contain this point. So then the wrappers of the F images would be all intervals from 0 to infinity for all of them. So it's not collapsing, yeah. Other questions? Yeah.
Then, so we find wrappers previously as closed intervals. Is there an issue with?
Right, so you always so the like an interval from 0 to infinity always has the infinity as like an open endpoint, but we'll just consider these types of intervals to also be closed. So it's possible that like this is a wrapper of something. Yeah. Okay, good. So what are the wrappers of these things? Yeah, exactly. So we'll just put a closed endpoint on the left and then it goes up to infinity. Okay, and then are these a collapsing collection for infinity? Yeah, because so they are a collapsing collection, right? Each one is contained in the next one, and there's no number that's contained in all of them. And in order to be a collapsing collection for infinity, you just want to see that infinity is the right endpoint of each of those intervals. So, this is a collapsing collection for infinity. So that means that we can say that the limit as x approaches 0 from the right of 1/x² is equal to infinity. Okay, what about as we approach 0 from the left? So let's say I instead wanted to do this calculation as x approaches 0 from the left.
what would be different? Well, we're squaring everything, so all the negatives will go away. Yeah, oh yeah, sure.
Is it necessary to do all of those steps besides like for the proof of it, since you already know if you plug in zero? It's gonna be like the nicest at that point, so if you keep squaring it, it's gonna grow. Like, does that make sense?
So which steps,
Like instead of doing, like creating the columns and collection, everything was just to find the limit from X of zero, like the function to the right. Is there a shortcut you could do that, just like check it off to know it's infinity by like. Since it's squared, it's not gonna be negative infinity, and then zero doesn't.
at this moment, like, this is what we have to do, but on Friday we'll have, like a better, like a shorter way to say.
Okay, so there are.
Yeah, there are shortcuts. Okay, awesome. Yeah. You're, no, you're sorry. Like the one thing, this, the first step is changing the stuff moving to the same. Yeah, that, exactly, so, the collapsing collection would be different, right? We would take a left-sided collapsing collection for zero, but then, we're plugging everything into 1/x², and so all of the negatives will go away, and we'll get the same F images and wrappers, and so we'll also get that the limit as x approaches zero from the left is infinity.
So we can just see like, by a similar argument, we get that the limit as x approaches zero from the left of 1/x² is equal to infinity as well. Okay, are there questions?
And just to spread this in my mind, the definition of continuity we talked about, when you say, so this, even though the limits are the same in both directions, you would say this still is continuous, but it's just for the reason that it's not defined at f of, zero, I guess here.
Yeah, so, right, so last time we said, if these two limits equal each other, then you can just say the limit as x approaches zero of this function is infinity. If that's also equal to the value of the function at zero, then you can say the function is continuous. But the value of the function can only be a real number, and so it's never gonna equal this. So it won't be continuous, no matter like, you know, how we decide to fill in a point. Yeah. Okay, good. So the next limit that we're gonna set up is limits at infinity. So we'll look at like limit as x approaches infinity of a function. So let's just go straight into the definition. Or maybe I'll just write an example quickly so you have like a picture in your mind of what we're about to do. So let's say f of x equals 1/x. Then we'll look at the limit as x goes off to infinity of 1/x. So let's say we plugged in some x values like 1, 10, 100, and so on. Then 1/x would be 1, 1/10, 1, 100th, and so on. So everything is trending towards zero, right? Everything's getting smaller and smaller. And so it sort of makes sense that we would have a way to say that the limit as x approaches infinity of 1/x is 0. So we'll just set up the definition for that now.
And it's gonna work exactly as you might expect. So now what we're gonna do is start with a collapsing collection for infinity, because that's what that's what's in this, what X is approaching. So we'll take a collapsing collection for infinity, compute the F images, take the wrappers, and then we wanna see that those intervals are collapsing collections for some value. And in this case, it'll be 0. Okay, so we say the limit as X approaches infinity of f of X is equal to some number L if, when we apply F to a collapsing collection of open intervals for infinity and take the wrappers, we get a collapsing collection for the number L. So the only footnote here is that we can make this same definition for minus infinity as well. So there, the only change would be that we would be taking a collapsing collection of open intervals for minus infinity. Okay, are there questions about the definition? Okay, let's do an example. So let's do this one. So we'll compute the limit as X approaches infinity of 1 over X. Okay, so I need to pick a open collapsing collection for infinity. So I'll just take the standard one for infinity. So it'll be the interval from 1 to infinity, 2 to infinity, 3 to infinity, and so on. Okay, what are the F images of these intervals? Yeah, so the first one would be like 0 to 1. So why is that?
Because one of the, like, it's just such a, like, 1 to infinity is such a small fraction, like, infinity is close to, and then 1 is 1.
Yeah, so as we plug in these numbers, right, the largest output of F will come when we put in 1, right? Everything else is gonna be, so here we have F of 1 is 1, but then as we move along in the interval, we'll just be taking 1 over larger and larger numbers, so we'll get things that are less than 1. And we're never gonna get a negative number, right? So we can get as small as we want, but we'll never go less than 0. We get this interval from 0 to 1. Are we happy with this? Okay. So then what would the next interval be? Yeah. Yeah, exactly. So here we get 0 to 1/2. Right, same reason. The largest output is gonna come when we put in this left endpoint. So we get 1/2 there. And then we would get 0 to 1/3 and so on. Okay, and then we'll take the wrappers. So since these are just each an open interval, we just change the open brackets to closed brackets. So we get 0 to 1 closed, 0 to 1/2, 0 to 1/3, and so on. And then, of course, these are collapsing collection, right? It's like the standard right-sided collapsing collection for 0. So these are a collapsing collection for 0. And so we can conclude that the limit as x approaches infinity of 1 over x is equal to 0. Okay, are there questions? Are you feeling comfortable with limits of functions? We have like a lot of different flavors, but they're sort of all, so we have like just limits of like left-sided limits of functions, right-sided limits, and then we can also, the limits could be infinite, and we can also look at the limit at infinity. But if you think about all these definitions, they're sort of all the same, just as like you're adding in infinity as options. Okay, so we will now talk about limits of sequences, because it sort of fits into this material about limits. So while limits are fresh in your mind, we'll look at limits of sequences, and we won't use them until integrals in like a month from now. So if it's not making sense right now, there's going to be time for it to settle in. But it's going to be pretty similar to limits of functions, so hopefully it's not too big of a jump. So look at limits of sequences. Okay, so what is a sequence? A sequence is just going to be a list of real numbers, an infinite list of real numbers. So make a definition. A sequence is an infinite list of real numbers. And a lot of times they're called A, so like A sub 1, A sub 2, A sub 3, and so on. And so I'll do an example. So we could have, for example, a sequence that looks like 1, 1/2, 1/3, 1/4, and so on. And it just continues on forever. So one way that you could write this is just by giving a formula for what the kth term would look like. So you could specify the sequence as, you could write A sub k, so the kth term in the list is given by the formula 1 over k. So if you want to know what is the 100th term in the list, you just plug in 1 over 100. And that would be the 100th term in the list. And it can be anything you want. So for example, you could have a constant sequence. So you could have like A sub k is equal to 3, and that would just look like an infinite list of threes. Okay, so hopefully like infinite lists of things are not a totally foreign idea because we've been looking at collapsing collections, which are infinite lists of intervals. So now we're just looking at infinite lists of real numbers. Other questions? So, in this context, it also sort of makes sense to say like, as I look further and further out in these lists, are the numbers approaching a specific value? Right, so like, in this list, as I go on and on and on and on forever, all I'm ever gonna see is threes. So you might wanna say like the limit as k approaches infinity of a sub k is equal to 3. And similarly, like for this one, as I look at terms further and further out in the list, I'm getting things that are closer and closer to 0. So there you might want to say that the limit as k goes to infinity of the sequence is 0. Does that make sense intuitively? Okay, so here is how we're gonna set this up. So I'll just say intuitively, we want to say something like the limit as k goes to infinity of 1 over k is equal to 0, and also things like the limit as k goes to infinity of 3 is going to be equal to 3. Okay, so we need now some slightly different tools than collapsing collections because here we're just taking like a discrete set of numbers rather than an entire looking at entire intervals of things. So here's how we will do this. So I'm going to define something called the tail of the sequence. So the picture you want to have in your head is that the sequence is like a snake, where the first term is the head of the snake. And we're going to top it off at the head. So that's what the tail is. So if A1, A2, A3, and so on is a sequence, then the kth tail, so this is going to be the sequence where we've just chopped off the first k terms. So you start at a sub k plus 1, and then go to a sub k plus 2, a sub k plus 3, and so on. So all we've done is just chop off first k terms. So in like the 1 over k example, so if a sub k is equal to 1 over k, let's look at like the third tail. So this is going to be a sequence where we've chopped off the first 3 terms of this guy. So 1 over 1 is chopped, 1 over 2 chopped, 1 over 3 chopped. So we're starting at 1 over 4. Does that make sense? Okay, so these are going to be sort of analogous to our collapsing collections for sequences. So what we're going to do is take the wrapper of the tails and see what happens to them. So, so I'll just write a definition of a wrapper of a sequence, but it's exactly what you'll think it is. So if A1, A2, A3, and so on is a sequence, then its wrapper, this is just going to be the wrapper of the set of numbers. I'm going to stick all of the numbers inside of a set. And we know how to take the wrapper of a set. So let's look at some examples of these wrappers. So let's say A sub n is just the constant 3 sequence. Then what is the wrapper of that sequence? Yeah.
It'd be closed interval.
Yeah, so this would just be, right, so I'm going to stick all of these inside of a set. So it'd just be an infinite list of 3s. Now with sets, you usually, so the set doesn't know how many times a specific number appears in there. So this is the same as just the set containing 3. So the set with infinitely many 3s is the same thing as just the set containing 3. Right? Because all a set knows is the element in there or not. Right? It doesn't know how many times it's in there. And then we're just taking the wrapper of this, which would, you could say it as it's the interval from 3 to 3. So we'll take the wrapper. But as a set, this is also just the same thing as the singleton containing 3, right? Because 3 is the only thing in there. Let's do the 1 over n example 2. So if A sub n is 1 over n, so our set now contains 1, 1/2, 1/3, and so on. What is the wrapper of that set? Yeah. Yeah, so you'd put it the other way because 0 is the smaller. Yeah, so we'll have an open 0, right? The numbers are getting closer and closer to 0, but never equal 0. Oh no, but it's a closed set, sorry. Wrapper. So closed from 0 to 1. Okay, good. Are there questions about these examples? Okay, so here's the definition of the limit of a sequence. So what we're going to do now is we're just going to take the wrappers of the tails. And if those are a collapsing collection for something, then that's the limit of the sequence. So I'm going to let L be a real number, or it could be plus or minus infinity. Then I'm going to let A1, A2, A3, and so on be a sequence. Then we'll say that the limit as k approaches infinity of A sub k is equal to the value L if the wrappers of the tails form a collapsing collection for that value L.
So what is happening here? We're taking the wrapper of the sequence, but then we're chopping off successive terms that we're just looking at what happens as you go out to infinity. And what you want to see is that those form a collapsing collection for some value. And then that means that your limit would be equal to that value.
And there's also just like by convention, there's some language for this. So if L is a real number, so just some finite number, then you say that the sequence converges. And otherwise, so if the limit, so if it's plus or minus infinity, or if it doesn't exist, so say your sequence is just like, I'll give an example. So, or if it does not exist, then we say AN diverges. So let's look at an example where it just doesn't exist at all. So basically this will come when, right, so your sequence isn't like trending towards anything, it's just bouncing around to a lot of different values. So here's the classic example. So let's look at this sequence that's just going back and forth between 1 and -1. Let me pause here and point out, like, how can you write a formula for this? Bouncing back and forth between 1 and -1. Yeah,
Like the sine of the, or sorry, cosine.
you could do it like that. So you're saying like, look, do like cosine of k pi or something. Yeah, so that's one way you could do it. Or maybe let's start with minus. No, wait. Well, okay, yeah. So if I do cosine of k pi, it'll start with a -1, so I'll just shift it. So I'll do k plus 1 pi. So that's one way that you could do it. The way that people usually do this is just by saying that this is equal to the number -1 raised to the k. So that will give you something that bounces back and forth between -1 and 1. But since we started with +1, we just need to shift this. So let's think about this for a second. So the first one would be -1 squared, which gives me 1. Second one would be -1 cubed, which is -1, and so on. So it'll just bounce back and forth between 1 and -1. Okay, so let's decide if this converges or diverges. So we need to look at the tails and then take their wrappers. So what are the tails in this case? So what will the first tail look like? If I chop off the head, what do I get? The first tail is just going to be, I would take this sequence and chop off the first value. So I'm just starting at the second value, which is -1. So the first tail would look like -1, 1, -1, 1,
-1, and so on. What would the second tail look like? Just chopping off the first two terms.
You just started.
Yeah, so you just start, so now those are chopped and we're starting here. And then for the subsequent tails, we're just gonna be switching back and forth between these two options, right? So the third tail would again look like -1, 1, -1, 1. Do you have a question?
Yeah. Is there ever like sub-zero or something, like just do the initial sequence, or would you not do that? You always have to count?
Yeah, you could say that that's like the 0th tail.
Would you use that? for any other numbers?
Yeah, yeah, we
Okay.
yeah. So yeah, so the list of tails will just go back and forth between these two things. So all we need to do is figure out what the wrappers of these two things are. So what is the wrapper of this one? Yeah, so this one will be -1, 1. And we get the same thing for the second one, right? It'll also just be -1, 1. Okay, so when I look at, so going back to the definition, the wrappers of the tails are all just going to be the interval from -1 to 1. So those do not form a collapsing collection for anything. So the wrappers of the tails are all -1 to 1. So, and this is not a collapsing collection. So that means that the limit does not exist. You could just write DNE for that. Okay, are there questions? I'll make one final comment, like how to relate this back to functions. So in a way, a sequence is a function, but it doesn't tell me what to do with every real number. It just tells me what to do with the positive whole numbers. So a sequence is a function. You could say f from the natural numbers, so n, this is 1, 2, 3, so on, to the real numbers, right? So given an input, which is one of these whole numbers, it outputs a real number. So my sequence a sub n would just be given by the value of f of n. So using this kind of thinking, you can graph your sequence. So we look at the plane, you know, you would just have like dots in your graph, right? So that would be your sequence. Let's say a sub n is 1 over n. And then with this setup, the wrappers of the tails are actually the wrappers of the F images of the standard collapsing collection for infinity. So secretly, we're sort of doing the same thing that we were doing with limits of functions.
Repeat this next.
Yeah, I'll write that down. So the wrappers of the tails are the wrappers of the F images of the standard collapsing collection for infinity, which would just be 1 to infinity, 2 to infinity, and so on. Okay, so in this way, limits of sequences are sort of the same concept as limits of functions at infinity. Okay. Okay, so we will end there, and on Friday we'll get into some improved tools for actually calculating limits.